Yeah, hi, it's Mark. So I'm kind of watching some of the episodes of a class that was given in 2020 at MIT by Professor David Kaiser, STS 042, Physics in the 20th Century. It's a lot of history of physics. And I'm currently on lecture two, which is about Faraday, Thomson, Maxwell, and lines of force in the ether. I'm particularly interested in the history of the ether because I think we got it wrong. And I think I can prove that we got it wrong. And I think we can explain why Michelson-Morley's experiment doesn't find it. I just want to introduce you, and I'm going to advance. I mean, there's just one section that I want to comment on.
Ah, good. There's a really interesting comment here from Sabrina. I like this. So Sabrina writes that I don't know what a gut is, a grand unified theory, but it seems like we're moving back towards everything being the same thing again. For some of these folks, the ether was a kind of word for something they didn't really know what it was. A subject, a topic they figured had to be everywhere because they could infer its effects. If I wiggle something here, something happens there. There must be some medium that transmitted the influence from A to B. If how could a moving bar magnet possibly affect an electric current? Because they're both immersed in the shared medium, this all-pervasive medium. And so they gave it a name. They gave it a name long before they had any kind of articulated descriptions or analogies of it. They called it the light-bearing ether, luminiferous ether, decades before they had any kind of more specific ideas about it.
Okay, so I want to comment on the ether. In the 1800s, David is saying that the scientists of the time thought there had to be some medium to carry things they were observing, like light and electromagnetic signals. So they imagined this thing called the luminiferous ether, which they later went on to disprove or interpret as disproved with the Michelson-Morley experiment. What I think is really happening here is there's been kind of a grand misunderstanding of how the universe works because I believe physicists missed something during the classical to quantum transition. And I think they missed the idea of constant rate point potential emitters. So there's like positive and negative point potential emitters that are like points, like geometric points, but they emit potential. Um, and they move around and they form assemblies, right? So they're flying around the universe, and depending on where they are, they might get subsumed into some high energy object and involved in a maelstrom of other high energy point potentials. They start forming things, right? Like they might form quarks or electrons or photons or neutrinos, or even the assemblies that make space-time. And I think I can make a very good case for this, that this is what's going on. The idea of a luminiferous ether is not a bad idea, but it's kind of different in reality. So our universe could really be described simply as these point potentials. And if you kept track of every point potential, like its current position, X, Y, Z, and its velocity, at the current time, and its polarity, positive or negative. And if you just kept that over a continuous path and then evaluated at every moment in time the action on each point potential that changes its future path, then what you would find is that that's all you really need to describe the universe at the lowest level. So you've got these point potential emitters constantly emitting potential, and that potential just flows through Euclidean space and time, like an empty void. You don't have to have anything more complicated for a medium than that when it comes to potential. But what happens is these assemblies start forming. And well, remember I said potential is moving through Euclidean space and time. Where's Einstein's space time? Well, it turns out, the Euclidean space and time is geometry one. That's like the baseline geometry. And then these assemblies form in certain conditions, like in supermassive black holes, that actually create space-time. So you can make out of 6 point potentials, three positive, three negative, you could make three orbiting binaries, and you could nest them together. And let's just assume that's how nature works. So you have three nested binaries kind of orbiting in different dimensions. You've got three dimensions to work with. It could be at angles, they could be precessing, whatever, but it makes like a little nucleus and they're all flying around. And, of course, the inner one might be dozens of orders of magnitude smaller in radius, higher in frequency, and higher in point potential velocity than the middle one. And then the outer binary in this nested tribinary, might be the slowest one, but it'll be the biggest orbit, the highest radius orbit, slowest velocity, lowest frequency. And so these things form a nucleus that is then reused in nature. Well, it turns out that these triply nested binaries, I call them Noether cores after Emmy Noether, who was an eminent scientist kind of back around in the early 1900s. He did a lot of work on conservation and just symmetries and so forth. I think it's very appropriate to name this assembly a Noether core. Anyway, that thing it becomes a nucleus of every standard model particle, and we are using one or more in every standard model particle. So, like for the fermions, they all have one Noether core. So they have 6 point potentials wrapped up in this triply nested binary. And they're decorated with 6 other point potentials to make the particular standard model assembly. And then photons, they use 2 Noether cores. You got the bosons, W's and Z's. They're kind of more ephemeral particles involved in a transition from one assembly to another. And then there's the Higgs boson. Well, so it turns out these Noether cores, when they're super high energy, when all three binaries are super high energy, they are extremely, extremely small, like smaller than the Planck scale. But as they get exposed to coming out of a black hole, they essentially become the particle assemblies of space-time. And they'll couple together a little bit, and they'll react and form all the other particles in the standard model. But most of them just come out of the supermassive black hole in each galaxy and become space-time. And they do everything you would expect them to do, according to Einstein, right? I mean, it's kind of like this perfect geometry. You've got three binaries that can tilt at any orbital angle. You can squish them if there's a lot of mass around, kind of transform them from Fermi-Dirac statistics to Bose-Einstein statistics. Um, there's just amazing things that they do. And guess what? I mean, that means space-time is kind of an ether, but in a different level of ether. It's an assembly-based ether. At the lowest level, every point potential emits potential which expands spherically forever. It's not impacted by anybody else. But when that potential intersects with other point potentials, action occurs. So that's the baseline thing of what's happening. You could evaluate the universe at every point in time in a continuous basis and just say, for every point potential, what are all the spheres of potential I'm receiving from all other point potentials in the universe, as well as possibly myself if I've gone faster than the speed of potential in the past. And then, you superimpose all those, you get the action. Except you could do that for every point potential in the universe. That's how it actually works. At t equal now, it's like synchronized, and then it just moves on through continuous time, through continuous space. Um, and that's how the universe advances. But these point potentials, what's so confusing, and this is our house of mirrors of nature, is that they form assemblies, and then these assemblies are what starts driving us crazy. We're trying to figure out, okay, well, how do we get to the bottom of the standard model? What's underneath the standard model? How do we unify the standard model, quantum mechanics, with general relativity? And so you can see that this assembly architecture, which would be below both of those theories, would provide the ontology that allows us to build up. And it makes it just a lot simpler to understand how nature and physics work, and hopefully make it a lot easier to simulate, and in some case, do some ideal analytical solutions. So I wanted to kind of mention this because I think the topic of the ether is so fascinating. David does a great job here telling us about the history, and I think it's good to augment that with what I think is the next era of understanding of nature.
They called it the light-bearing ether, luminiferous ether, decades before they had any kind of more specific ideas about it. And so in that sense, I think it is kind of like we're in a similar situation today with our quest to understand what's the world made of. And we have very finely articulated models like a standard model, and this kind of neutrino and that kind of electron, and up quarks and down quarks, and gluons and Higgs, I mean, all this very specific stuff. And that amounts, as you may know, for not more than 5% of the kind of mass balance of the universe. We've explained 5% of the universe with unbelievable precision out to 12 decimal places. Thank you very much. And we know nothing, with a capital N, nothing about the other 95% of the energy balance. So we give it names. We call it dark matter and dark energy. And I think in some sense, I have some sort of sympathy with either my present colleagues and myself, and or with the kind of people of Faraday's and Maxwell's age. They didn't know what the ether was, but they knew it had to be there. It was conveying all these effects. They could measure the effects of disturbing the ether as far as they were concerned. So they gave it a name, a kind of placeholder name, partly to help organize their studies. Oh, I'm studying the luminiferous ether as well. That helps get scholars on the same page. They would give their best estimates of what they thought the thing was like and how it would behave, but they didn't know, right? They had better or less compelling responses. And I think we're in a very similar situation today, not by design, not by our hopes, but because we have been stymied now for decades to get any more kind of carefully articulated knowledge about what specifically is dark matter that seems to be filling every galaxy much, much more so than ordinary matter. What particularly is this other separate kind of stuff that we now call dark energy. So I think I don't want to say we've learned nothing since 1820, but we can see some maybe humbling, humility-inducing parallels between our best efforts today and the efforts of very, very earnest, talented folks from long ago.
All right, that was a really nice discussion by David. I really appreciate it when scientists kind of do self-reflection and look at their field and perspective and like what they know and what they don't know. Truly honest about it. I still think scientists, physicists haven't really figured out some of the bigger issues that they're going to need to go back and look at look for something they missed before general relativity and quantum mechanics. It's like, they've got those and they are steeped in that kind of mathematics and knowledge and measurement observation, but it's very difficult for them to kind of just set all that aside as a reference model and go back and look for some different solution that they might have missed. But let me show you a couple ideas here. So this is a primitive visualization of a Noether core just to show you the three binaries. You can see there's a binary on the inside here with a minus and a plus point potential, and they're orbiting. Again, each of these binaries can be vastly different orders of magnitude of radius, frequency, energy, so forth. But, we show it all here. You just kind of imagine this as logarithmic in terms of size. Then there's a second binary orbiting here around the internal binary, and a third binary, again, at lower energy, lower frequency on the outside. And this is another core. And I'll show you in a minute a true animation of this. But it's just got so many amazing characteristics. One is you see these flux tubes coming out, which is, if you can imagine the orbital axis of one of these binaries, it's going to be kind of a maelstrom of electrical potential changing very quickly. That leads to a lot of really interesting characteristics. David is talking about that we only know 5% of the matter and energy in the universe. And I want to observe that these Noether cores are extremely stealthy. And why are they stealthy? There's several main reasons. One is that the emission is constant rate from a point potential. So that means at any given point, when it emits its potential that becomes a sphere of potential expanding forever, the amount of potential that's emitted at any given point in real space and time on the path is divided by the velocity. So that means the faster it goes, the smaller the sphere stream is going to be as it first emits. So going really fast, it's going to be really small to begin with, and the magnitude will be small. So that means as it expands and falls off at 1 over the radius, it's going to be even smaller. So, that's going to be hard to detect for a fast-moving point potential. The second is that the frequencies of these point potentials are so high that they're well beyond our ability to observe today. And the third is that somehow these three binaries present a very low footprint in the potential field. There's only one field in this model, this potential field. So through superposition, which is a normal, everyday, well-known part of physics, the potentials emitted by the inner, middle, and outer binaries here will tend to cancel around the Noether core and just present very, very little mass or apparent energy. So if we're looking for 95% of the mass and energy in the universe, I would argue that most of it is inside of these Noether cores. Um, the Noether cores that make you and me and planets and stars and so forth, that's a minority of the Noether cores in the universe. Most of the Noether cores in the universe are packed into space-time assemblies, which is made out of these Noether cores, and they're extremely small and extremely dense. They pass right through us. They pass right through everything. Pretty much, that's where I would look. And you know, I'm suggesting that these Noether cores emit out of supermassive black holes because it's a recycling universe, and for the most part, the point charges and energy in a galaxy just stay within that galaxy. They emit as fresh space-time. They become other particles. They become space-time that is expanding once they emit from the supermassive black hole in a galaxy. And then essentially they just recycle over the eons, right? They might go right back into the black hole, or they may shoot out and, you know, go to the edges of the galaxy, or some of them shoot out, as neutrinos or photons or whatever that fly off out of the galaxy and into intergalactic space. But I think you'd have to argue that most of them stay within the galaxy. So that's why I would look for dark matter and dark energy. It shouldn't be a mystery. If we hadn't missed the solution to nature 125 years ago during the classical to quantum transition, we would know all about this. Now, let me show you some more about the Noether core. What I'm trying to show with this slide is, here I have kind of a flat imagination of the Noether core. It's not really showing its full three-dimensional capability, but you can see the three binaries that are nested. And what I'm trying to show is this is an incredibly scalable architecture, right? And uh, you don't even have to think about these as just gradually growing by from 1 to 2 to 3. This could be, from like 1 to 10 to 100. Each additional one here, this can all be logarithmic. This assembly can just scale over many, many, many orders of magnitude. And that's essential to delivering some of the things that Einstein said space-time should do, because these Noether cores, as I said, are used in the assemblies of space-time. And they're also used in the assemblies that make the standard model particles. And you can imagine as energy increases, these Noether cores get smaller in diameter, higher energy, higher frequency. But as they get smaller, you're starting to see that contraction, right, of Einstein. And there's also another factor, which is, they're really three-dimensional. As they get more oblate, that's going to change how we perceive time inside of Einstein's spacetime. It's a different kind of time than just the absolute time in the background. Um, anyway, that's a little bit more about how Noether cores work. All right, so this is an animation of the point potential architecture. The object in the middle with the rotating red and blue point potentials, that's the Noether core. And you can see there's three binaries. I tried to animate it with different speeds, if you can see that. Uh, this also shows kind of the generalized fermion architecture, which is then kind of at a whole nother order of magnitude there will be personality point charges captured in the poles of each binary. Of course, this is just a simple animation. This isn't a simulation, but presumably there's a lot more going on in terms of precession and motion, and depending on how much energy, how much thermal energy is involved, I think this could be quite dynamic. But I think this is the basic architecture of what's going on. Those six polar personality charges, like for example, if they were all blue negative point potentials, that would be this. This would show an electron, um, and you can make quarks. The main thing I wanted to show you here is how the architecture works in that central Noether core. That, of course, physics, they're kind of aware of it, but not kind of not aware of it because it's the heart of so many things they do, but they just don't know. I mean, they're off in an ontology that involves fields. And they're not working with point potentials. But that Noether core, of course, is responsible for the generations in the standard model, the generations of quarks, the generations of the electron, electron, muon, tau, you know, up term top in the quarks, down strange bottom in the other kind of quark. Even the Noether core is responsible for promatter and antimatter. That's just a different configuration and a different precession of the Noether core that makes antimatter different than regular promatter. Anyway, I want to show you what the Noether core is so you have something tangible to think about. Hope you enjoyed this video. I just wanted to talk about the Aether a little bit. And thanks to David Kaiser for making some really good points that I could talk about. Bye.